Hello. So in this lesson, we're going to talk about two theorems that relate to the division of polynomials, the remainder theorem and the factor theorem. So in this table here, we see several polynomial functions in the first column, and we see the output values for the input values that are listed in the second column. And we also see in the last column the results of the polynomial division that we're going to look at right now. So here in the first row, we have f of x equals x squared plus 5x plus 1. Now, if we take f of 1, this tells us that f of 1 equals to 7. And here, this is actually the area model for x squared plus 5x plus 1 divided by x minus 1. And so this gives us an answer of x plus 6 with a remainder of 7, which we can express as 7 over x minus 1. And so we notice here that f of 1 equals 7. And when we divide by x minus 1, we get a remainder of 7. Similarly, in the second row, f of 2 is equal to negative 1. And when we take x squared plus 2x minus 9 and we divide by x minus 2, we get some quotient. In this case, it's x plus 4, plus negative 1 over x minus 2. And again, this remainder, negative 1, is equal to the output value here. And so we see this pattern actually for all of the functions here, that f here, here, and here. And in this case, we sometimes get f of a equal to 0, and also we get no remainder here. So this illustrates a theorem that we call the remainder theorem, namely that if we take a polynomial p of x and if we divide it by an expression in the form x minus a, where a is a real number, then that remainder of that division equals p of a. And the last two rows illustrate what we call the factor theorem, which says that if we take a real number, a, that's 0 of a polynomial function, and remember, a 0 of a function means that if a is a 0, that means that p of a equals 0. Then x minus a is a factor of p of x. So basically, if a real number a is a 0, that will give us a 0 remainder. That tells us that x minus a is a factor. Now we can apply these theorems in examples like the following one. And I think it's a little easier to understand these theorems when we see them in practice with these examples. So we need to find the remainder when this polynomial is divided by x minus 3. Now we could just divide this and then find the quotient and then find the remainder, but that takes quite a bit of work. And so with the remainder theorem, it is easier, I think. We can say if we call p of x equal to x minus x to the third minus 4x squared plus 5x plus 3, then that quotient p of x over x minus 3 has a remainder equal to p of 3. Now you notice that the remainder theorem says that if we divide by x minus a, then p of a is the remainder. And what that means in practice is that if we are dividing by x minus 3, then the remainder is equal to p of positive 3. We're basically flipping the sign. And the reason why we're doing that, if you recall, is that when we first started talking about factors of polynomial functions in factor form, if the 0 is, say, 3, then the factor that gives us that 0 is x minus 3. Right? And so we flip the sign there to go from the 0 to the factor. And it's the same rule that applies here. And so what we do here is that we can then calculate P of 3 by substituting into the expression. So we put, instead of x, we put 3, and we put that in parentheses to clearly indicate that we're substituting that. And when we do this, we can do this by hand or in a calculator, we'll get that P of 3 is 9. And so that's our answer. That's the remainder when we divide x to the third minus 4x squared plus 5x plus 3 by x minus 3. Now, this is a different type of question here. Is x plus 1 a factor of f of x here? And let's justify our answer. Now, justify our answer means that we need to write some kind of clearer explanation of our work. We don't just write the calculations. And so what we're going to do is we can say that by the factor theorem, if f of negative 1 equals 0, then x plus 1 is a factor of f of x. And we like to write this sentence just to be really absolutely clear in our explanations. We don't want to say as an explanation, well, we plug in or we substitute negative 1 for x, because that kind of tells us what we're doing, but it doesn't really explain why we're doing it. So here, what we can do is, again, we can substitute and we can get f of negative 1. And so f of negative 1 is 2 times negative 1 to the 5th minus 4 times negative 1 to the 4th plus 9 times negative 1 to the 3rd minus negative 1 plus 13. And when we get that, we will see that this is negative 2 minus 4 minus 9 plus 1 plus 13. And when we work this out, we see that this is negative 1. But it's not 0. So because it's not 0, then we may conclude that x plus 1 is not a factor. Because if it were a factor, then f of 1 would equal 0. It wouldn't equal anything else. Now, number 9 is a different type of problem. And at first glance, you may look at it and say, well, what does this have to do with the remainder theorem? But we see some key words here that tip us off that we're dealing with the remainder theorem. We have a polynomial divided by a binomial in the form x minus a. In this case, a is equal to 1. So we can write that down. The remainder is 8. Now, the remainder when we do that division is 8. That tells us that we can apply the remainder theorem. So let's see what we know by the remainder theorem. If p of x is x to the third minus k x squared plus 2, p of x divided by x minus 1 has a remainder of 8. Well, sorry, by the remainder theorem, we know that p of x over x minus 1 has a remainder of p of 1. We also know from what's given to us that p of 1 equals 8. So we can actually set these two expressions equal to each other. So p of 1 is equal to 1 to the third minus k times 1 squared plus 2. Because that's what p of 1 means. We substitute 1 for x. But we also know that p of 1 is equal to 8. So now look at what we have. We have an expression with k and a bunch of numbers equal to 8. That's an equation that we can solve for k. 1 to the third is 1, minus k times 1 squared is k, plus 2 equals 8. We can combine like terms. and get 3 minus k equals 8. Subtract 3, and we get negative k equals 5. And if we divide both sides by negative 1, we get k equal to negative 5. So that tells us that x to the third minus negative 5x squared plus 2 divided by x minus 1, which is x to the third plus 5x squared plus 2 divided by x minus 1, has a remainder of 8. So our answer here is k equals negative 5.